Sometimes the biggest revolutions in science don't start with some huge explosion, but with a tiny little spark that just doesn't make sense. We're about to dive into a simple experiment that had the greatest minds of a century completely stumped, and we'll see how a young patent clerk named Albert Einstein solved it by basically tearing up the entire rulebook on what light even is.
All right, so what was the big mystery? Why did shining a little bit of light on a piece of metal completely break physics? I mean, it sounds so simple, right? You shine a light, and it can knock these tiny particles called electrons loose. But the way it happened, the strange, almost picky rules it followed, it defied everything physicists thought they knew.
It all kicked off with this really baffling spark, a phenomenon we now know as the photoelectric effect.
So way back in 1887, a physicist named Heinrich Hertz noticed something kind of weird. When he shone light, especially ultraviolet light, onto a metal plate, it would create a spark. The light was literally kicking electrons right off the metal. It was a super direct interaction, light in, electron out. And that's the textbook definition, right? The photoelectric effect. Those electrons that get kicked out, they're called photoelectrons, which is really just a fancy way of saying light electrons. But this super simple effect was hiding a massive, massive contradiction.
So, to really get why this was such a headache for scientists, you've got to understand what they thought light was at the time. And let me tell you, their favorite theory was about to slam into a brick wall.
Okay, so for a long, long time, pretty much everyone agreed light is a wave, a continuous wave, kind of like ripples in a pond. And just like a huge ocean wave has way more energy than a tiny ripple, physicists thought that brighter light, more intense light, must carry more energy. Makes total sense, right? Well, it turned out to be completely wrong. And this is where the whole wave theory just falls apart. I mean, look at this. On one side, you have what the theory predicted, and on the other, what actually happened. Prediction number one, a brighter light is a stronger wave, so it should kick out electrons with more energy, right? Nope. The reality was, brighter light just kicked out more electrons, but the energy of each one had nothing to do with brightness. It only depended on the light's color. Okay, prediction number two. A really faint light should take a while to build up enough energy to free an electron. But again, wrong. Electrons popped out instantly, no matter how dim the light was. And the final nail in the coffin. The theory said any color of light should work if you just make it bright enough. But experiments showed a hard cutoff. For some metals, you could blast them with the most intense red light imaginable, and nothing. But then, the faintest little glimmer of violet light would work immediately. Physics was completely and utterly stuck.
And this is where our main character walks onto the stage. It's 1905, and a young Albert Einstein, who's working a day job at a patent office, of all places, comes up with a solution. And it was so radical, so out there, it would change physics forever.
This is the paper he published. And I love this. Notice how he called it a heuristic viewpoint, not some grand theory. It was his way of saying, hey guys, I don't have all the answers, but what if we've been thinking about light all wrong?
And this quote right here, this is the core of it. Einstein basically said, what if light isn't a continuous wave spreading out smoothly? What if it's made of a finite number of energy packets? He was suggesting that light acts less like a wave and more like a stream of tiny microscopic bullets.
So this crazy idea needed a new name for this particle of light. And with it, Einstein didn't just have a cool idea. He had the perfect key to unlock the whole photoelectric mystery. Those energy quanta he talked about, well, later on, they got a much catchier name, the photon. This is it, the fundamental particle of light, a single indivisible packet of pure energy.
So how does this photon idea fix everything? Okay, let's walk through it. 1. Light isn't a wave. It's a stream of these little photon packets. 2. Here's the kicker. A photon's energy depends only on its frequency. Its color. A blue photon has more energy than a red one. Brightness, that just means you have more photons, not more powerful ones. 3. When light hits the metal, it's a simple one-on-one collision. One photon hits one electron. That's it. And 4, if that single photon has enough energy to overcome what's called the work function, that's kind of the energy gluing the electron to the metal, bam, the electron is knocked free instantly.
Einstein even boiled this whole concept down into this beautifully simple equation. You can think of it like this. The energy the electron has when it flies off is just the energy of the photon that hit it, minus a little escape fee the electron had to pay to get out of the metal. That phi is the work function. It's so clean, so precise, and it explained everything they were seeing in the lab perfectly.
And just like that, with the idea of the photon, all those baffling mysteries just evaporate. Why does the electron's energy depend on the light's color? Because the photon's energy depends on its color. Why is there no time lag? Because it's an instantaneous one-on-one deal. There's no waiting around. And why is there that threshold frequency? Well, a photon needs a certain minimum energy to pay that escape fee. If a red light photon can't afford the cover charge, it's not getting in. It doesn't matter how many of its friends show up. Case well and truly closed. But here's the thing. Einstein had done way more than just explain a weird little spark. He had basically fired the starting pistol for a whole new kind of physics. Yeah, this is so much bigger than just one experiment. This wasn't just fixing a bug in the old theory. This was a complete paradigm shift in how we see reality. This idea that energy itself comes in these little discrete chunks, these quanta, that's the absolute bedrock of all of quantum mechanics.
And you can really see the story unfold on this timeline. You have Hertz stumbling upon the effect in 1887, then Max Planck in 1900 first whispers the idea of energy packets to solve a totally different problem, but it was Einstein in 1905 who made the huge leap and said, no, wait, light itself is made of these packets. His idea was so out there, it took until 1914 for Robert Millikan's experiments to prove he was right. And get this, it was for this discovery, for the photon, that Einstein won his Nobel Prize in 1921, not for his more famous theory of relativity.
I mean, the legacy of this one idea is just staggering. It proved one of the weirdest things about our universe, that light is somehow both a wave and a particle. That's called wave-particle duality, and it's a cornerstone of quantum physics. But it's not just some abstract theory. This is the very reason solar panels work. It's how the sensor in your camera, in your phone, literally turns light into a photograph. It's all because of the photon.
So let's end with this thought. The photoelectric effect showed us that on the smallest scales, the universe doesn't really care about our common sense. It plays by its own, much stranger rules. And it really makes you wonder, right? If something as everyday as light can hide a secret this profound, this bizarre, what other game-changing ideas are out there, just waiting for the next little baffling spark to reveal them?